Have you ever really stopped to think about water? The journey it takes to even get to you? Well, it turns out it's this epic trip, and it's all run by these invisible forces and, well, some pretty powerful laws of physics. So in this explainer, we're going to pull back the curtain on the secret life of water and really get into the nitty-gritty physics that tells it where to go and what to do.
So let's start with a really simple idea. What if just one single drop of water could tell us its story? We're going to follow that one drop on its incredible adventure, all the way from its birth up in a cloud, through wild rivers, into the maze of pipes under our feet, and right to the very end, coming out of your tap.
And to really get this story, we're going to need a couple of secret weapons from science. First up is fluid mechanics. That's just the study of how fluids, like our water, move around. And the second is hydrology, which is all about how water gets distributed and managed here on planet Earth. You put those two together, and we can unlock the whole story of our little water droplet.
Okay, so our droplet story starts way, way up in the atmosphere. Right now, it's not even a drop yet. It's just vapor. Let's see how it makes the leap.
So our droplet officially begins its life as precipitation, right? Rain. And that can happen in a few different ways. You've got convective rain. That's when the sun heats the ground, warm, moist air shoots up, cools down, and boom, rain. Then there's orographic rainfall, which is just a fancy way of saying mountains get in the way and force the air up. And finally, cyclonic rainfall. That's what you see in big weather systems, where all that moist air gets sucked into a low-pressure zone.
But what actually holds this brand new water droplet together? Well, it's this amazing force called surface tension. The best way to think about it is like an invisible, stretchy skin on the water. It's all the water molecules pulling on each other super tightly. And this force is so powerful, it pulls the droplet into a perfect sphere, which just so happens to be the most efficient, compact shape possible in nature. Pretty cool, right?
And, this isn't just some vague idea. We can actually calculate the pressure squishing that tiny sphere. The formula here, P equals 4 sigma over D, tells us something really fascinating. It shows the pressure all comes down to that surface tension, the sigma, and the droplet's diameter, D. And this leads to something you might not expect. The smaller the droplet, the crazier the pressure is inside.
Okay, another super important property we have to talk about is viscosity. It's basically just how much a fluid resists flowing. You can think of it as its internal friction. I mean, just picture pouring water versus pouring honey, right? Honey is way, way more viscous. And this property, it's going to affect everything about how our droplet moves and bumps into things on its way down to Earth.
And touchdown. Our droplet has landed. It's joined up with trillions of others, and now it's part of a stream, or maybe a river. This is what engineers call an open channel, and believe me, it is a whole new world with a completely different set of rules.
So, what's the deal here? What makes one river a slow, lazy stream you could float down all day, and another one a chaotic, raging rapid? I mean, figuring this out is absolutely critical if you're trying to manage a waterway, and the answer is actually simpler than you think.
It all comes down to one little number, the Froude number. Okay, imagine you toss a rock into a stream and watch the ripples. The Froude number is basically just comparing how fast the river is flowing to how fast those ripples can spread out. That's it. And that one simple comparison tells us everything we need to know about the state of a river. And that number gives us two totally different states of flow. When the Froude number is less than 1, we call that subcritical flow. It's calm, it's deep, it's slow. In fact, it's so chill that waves and ripples can actually travel upstream against the current. But when that number jumps above 1, things get supercritical. It becomes fast, chaotic, shallow. Any wave that tries to form is just instantly swept away downstream. Total opposite.
But the journey isn't over. Our little droplet gets pulled from the natural river and enters this hidden world of our infrastructure. We're talking about a massive, man-made network of pipes, all designed to bring it closer to our homes.
All right, the first rule of pipe flow is something called the continuity equation. It's really just a simple but super powerful idea. What goes in must come out. For a fluid like water, it just means that the amount of water you push into one end of a pipe has to be the same amount that comes out the other end. Makes sense, right?
And this simple equation leads to something you've definitely experienced. You know when you put your thumb over the end of a garden hose? You're making the area smaller. So to get that same amount of water out, the water has no choice but to speed up. It's this perfect trade-off, and it's how you turn a gentle flow into a powerful jet of water.
Okay, now for one of the rock stars of fluid mechanics, Bernoulli's equation. The best way to think about it is like an energy budget for our water droplet. It's a basic law of energy conservation, and all it really says is that for a fluid that's moving, its total energy has to stay the same. It can't just appear or disappear.
So this total energy is made up of three parts. First, you've got pressure energy. That's basically how much the water is being squeezed. Then there's kinetic energy, which is just the energy it has from moving, from its speed. And finally, you have potential energy, which comes from how high up it is.
And because that total energy budget has to stay balanced, if you change one thing, something else has to give. So if the water suddenly speeds up, its kinetic energy goes way up. Well, that energy has to come from somewhere, right? So its pressure or its height has to go down to pay for it. This is the exact same trade-off, the same principle that allows an airplane wing to generate lift and fly.
So we've followed our droplet, we've learned the physics that boss it around. But how do engineers actually use all these rules to manage water for, entire cities and massive farms?
Well, they turn this theory into real-world practice every single day. To measure how much water is flowing, they'll use something called a ventrometer. It just creates a little bottleneck in a pipe, which makes the water speed up. They measure the pressure drop, and using Bernoulli's principle, they can calculate the exact flow rate. Of course, they also have equations to deal with reality, like energy loss to friction in pipes, and they use hydrology to predict how big a flood might be after a heavy storm.
And this really brings us full circle, back to our main idea. This whole incredibly complex journey of one water droplet, all the way from a cloud, into a river, through a pipe, and finally to your home. It's all governed by these same elegant, fundamental laws of physics.
So, we figured out how to understand, predict, and even engineer the journey of water with amazing precision. But all this knowledge, all this mastery, it kind of raises one last and maybe more important question. Knowing how water works is one thing, but can we use that same knowledge to protect it? To make sure this incredible resource is there for a future? That's really something to think about.